I don't think Intel SGX was out yet, but we were kind of like playing around with how can we actually have like trusted execution environments, like the secure execution environments, where you can run certain workloads within it as it has integrity and confidentiality protection. So that's like more than 10 years ago. So yeah. So basically today, the presentation that I'll be giving is like how to share a little bit about our work on how we can have a Web3-based DCAP. So I think Andrew made a really good presentation just now on like what DCAP is about, and how right now, although DCAP is poised, because Intel provided us with all the tools where we can remove Intel from the kind of like the attestation workflow. And in this presentation, I will kind of like share how we go about it. So I think the first thing that we need, if we think about like attestation, there's actually kind of like two portions of it, right? One of it is the verifier, and the other one is the verifier, of course, is the one that verifies the report, the code, and produce a result, whether is it genuine, is it trusted, and the other portion is actually the infrastructure that surrounds it. So the first thing, let's say if you want to do verification of the DCAP attestation, say on Ethereum or any of the EVM chains, then we need a solidity-based verifier. And so we actually wrote an on-chain verifier, call it the Automata DCAP V3. I know it's a very boring name, but I'm really bad at it, so this would have to do. So what it does is we have implemented all the logic of the report verification on chain. Of course, the assumption is that during the generation of the report, the collaterals are actually available to the users, and any missing collaterals will actually have to be placed onto the contract itself. So what we have is actually we have a kind of like structure like that, where each individual project who wants to perform such an attestation can actually choose to clone our repo, deploy it on chain, and provision certain configuration like the application hash, the MR enclave, the developer signing key, which is the MR signer. And stuff like TCB info that Andrew mentioned about the collaterals, like the intermediary certs. The person that is deploying the contract will have to actually perform all of this. And if you think about it, there's no check about it, because the owner is the one that is actually provisioning all these collaterals. So this is actually what we have now. But we kind of like realize that it's a bit problematic, because the thing about Web3 is that it should be like open and then composable, and this isn't really very composable. Each time someone wants to do something new, upgrade the software or rely on something, they have to do this whole process, and the collaterals aren't shared. So if I have a machine and I participate in like two different, I run two different enclaves on my machine, then I have to like attest myself to two different contracts. This is not very usable. So like, how can we make it better? Well, the thing is, we first need to understand like what we mean by verifying a remote like attestation report. There's actually two portions to it. The first, we can kind of like break it down into two portions, where the first part is we verify that the report itself is genuine and authentic. That means we can trust the content of the report. And subsequently, based on the content of the report, we can have certain so-called business logic to determine what we want to do with the report. So, for example, in terms of like verifying the MR, the identity of the application, the enclave application, we can say that, hey, we first ensure that this report indeed comes from a genuine Intel SGX or TDX machine. Then, once we have verified that this report is genuine, then we can do things like, oh, let's check the hash of the enclave. Let's check the TCB of the enclave, so on and so on. So if we kind of like think of it this way, then we can have a much simpler, instead of one single like verify interface where we return the boolean, we can break it down into like two interfaces. One of it is to actually verify the code, and once the code is verified, we will extract like the important information, content of the code, and this content, this verified result will then be used by downstream processes to actually obtain the result of whether this is indeed the enclave that I want to do the right thing. So, I mean, with that we can come up with this like verify and attest with a code, and what we have is actually instead of having multiple contracts, we can have one single verifier contract that is deployed on any chain that wants to support like DCAP verification. The code can then be sent on chain. That single contract will collect all the different collaterals that we can find, like the TCP info and the intermediate certificates, and then the results of this contract will then be used by all the different downstream users. So, for example, in like for Automata, we have our 1RPC endpoint that uses hashtags enclave. So we can say that there's this particular MR enclave that we are interested in, and it's going to verify it. And Flashbots might have a Sierra, MR enclave, and similarly, they can do their own verification. All of us can share this single verifier. Then, that's great already, right? But then, like, on-chain verification is really expensive. Like, we actually make it cheaper. Like, in order for us to verify a single code, it takes about 3 million. Yes, I mean, it's doable, but it's really expensive. So the thought of us is that can we actually make it cheaper by offloading the computation to a kind of like off-chain compute platform, and then the computation is then verified using a succinct proof. So, and what do we know? Like previously when we break out that verified boolean, if we originally keep it as a simple, like verify and return boolean, then every time we have a new MR enclave, we'll need to write a new ZK circuit. But since we have already separated out like the verification portion and the business logic, now we can actually have like kind of like a common interface where we can have verify and attest on chain if we want to perform everything on chain, or if we want to make use of a ZK proof. And the output of these two kind of like interface will be the same. It will be the verified output that the kind of like downstream applications can use. So like kind of like add into the overall architecture. Now we have the ZKP and then this on-chain, a succinct proof basically. So Andrew actually mentioned something that is during the code generation process, the enclave actually need to compact this software called the PCCS. Now the thing is, the PCCS by default actually fetches the information from Intel's PCS, which is the kind of like source of the information. But the thing is, not all collaterals can actually be found on Intel's PCS. If you are working with like cloud providers, like you're running SGX or TDX instance on Azure, for example, then the collaterals for those machines, you won't actually find them on Intel's PCS. Rather, you'll find them on Azure's own kind of like PCS service. So depending on what kind of hardware and where you're running them, you actually have to go to different places to look for like your collaterals. Can we do better? Of course, we can like what Andrew mentioned, we can put it onto the blockchain, and this is exactly what we did. So what we did is we wrote a code provider library. So when the enclave, when they actually wants to kind of like generate code, generate a report, what it does is it will contact this library that's installed as part of your SGX setup, and this code library will be the one that's responsible to fetch the collaterals from the PCCS. So what we did was to actually write a DCAP code provider library that will fetch the corresponding collaterals instead of PCS actually from an on-chain contract. And on the on-chain contract, we actually implemented the full schema for the PCCS. So basically, it's a one-to-one mapping of the PCCS schema. So we have stuff like PCK DAO, TCB DAO, so on and so forth. And basically, what we have then now is that we have a total kind of like attestation framework where on-chain we have a database of all the different collaterals, and like when we want to upsert a particular collateral, we will just perform the corresponding check that a standard PCCS would do to ensure that the cert chain is being signed. Similarly for TCP info, and all this information is read by the like we call it automata DCAP 2PL, but we can call it Web3 2PL to make it more true. And the nicest part of it is that now our verifier don't have to maintain the collateral anymore. The verifier itself can actually read on-chain from the on-chain PCCS, obtain the collaterals, and then verify it. And this actually allows us to do more interesting thing. Instead of including the collateral as part of the code, your code now can actually be generated offline without any internet access. So your offline what's that called? Enclave can generate a code. We will take this code and then just directly verify it online. And because we have a on-chain PCCS, the verifier is able to actually fetch the collaterals totally on-chain without the need to access any like extrinsic external sources of information. So finally, we have an architecture something like this. We have a verifier that talks to the on-chain PCCS that contains the collateral, accepts like on-chain verification or off-chain verification of the code, and downstream kind of like applications can use of it. So, So basically, that's the end. What we have done is currently the open source version of our DCAP verification, DCAP attestation contract is actually for V3 only. This is for Intel SGX only. We have actually implemented the version 4 of the code, which includes TDX verification also, and all of this is also kind of like combined with the ZK proof portion of it. That means you can actually verify the attestation of chain, and this is done via RISC-0. And the on-chain portion of it is actually the PCCS. Now, the thing about the PCCS is that we need help to actually kind of like populate the PCCS. It is a caching service. So the way how it works out is that if there is a code that has missing collaterals, we would actually push the collaterals on chain. But I actually open this up to everyone in this room. I hope we can kind of like have a Web3 maintained PCCS, and you can keep that PCCS service as updated as possible. And this way, anyone who needs to use this PCCS service can now just rely on this, and there's no need for us to like require our enclave or our operators to run like custom PCCS service, register with Intel to get an API key, find out whether we need to register again with Azure to have a separate like PCS from Azure or with GCP. So that's about it. I'm open for questions. Thank you so much.
Well, I guess if there's any questions, feel free to ask Zheng Leong here also for this presentation today. Okay, well, maybe one thing, I'm also going to, well, any questions first? Take one question. Okay, great. And then what we'll do is, I'm continuing to reorder the programming, because I know that there's some interesting things from funding class that will be nicely fit into these couple presentations, and then we'll go into use cases.
So quick question. In my impression, the collaterals would be very huge for example, for every like a batch of the CPU, they would have their own collateral. So I have the impression, but maybe I'm wrong. So basically, for every like a few hundreds or few thousand CPU, they're going to be their own collateral. So have you like measured how much this will be, and if you put all of them on the blockchain, how much like storage it will occupy?
So this is an interesting question. We have actually measured it. Typically, for most search chain, it will be about 1 kilobyte, 1 to 3 kilobytes big. Now the thing is, actually a lot of the intermediate certs are what's it called? Are replicated, so to say. So you have a PCK cert, and then you have an intermediate cert that signs the PCK cert. So the intermediate cert is actually the same for nearly all the different leaf PCK cert. But I don't think that would be a big problem, especially if like we do it in a distributed manner, and then like whenever we need it, we will push the cert information on chain. So yeah, we are actually using it ourselves now for the verification of the machines that we are using.
So probably it will also be some kind of cache because the collaterals will also like duplicate over the time.
Yes, correct. So that's why there's a need to actually maintain this cache.
Cool, thanks.